So the sun is 93 million miles away from the Earth, and it's a big, important life essence to keeping the Earth in its orbit and supplying it with sunlight. Plants need photosynthesis. And, it's just a big, massive ball of plasma. But at the end of the day, there are still mysteries about the sun that haven't been solved. Or maybe we have, like, really common facts about it, and yet maybe there's still some things that most people don't look at. So hopefully with this video, here's 10 things that you probably didn't know about the sun, but you might know a few of them here and there. We start this list with probably one of the more easier ones to understand, but over time you can really see like how something like this could go a far way. The hydrogen in the sun is the most common element in its core or in its whole system. And then the second one is helium. Now, hydrogen is 91.2% roughly, and for helium it's roughly 9%. Somewhere in the sun's lifespan, they say that after all the hydrogen is disappeared, it's all gone, it'll be converted into helium. And if you don't know, helium obviously is a gas element that inflates things. So most of the helium that is inside of the sun is going to inflate up like a balloon. It's going to be what is known as a red giant or a super red giant. I have to double check which one, but it's going to be bigger than it is now, basically. And what that essentially means is it's red giants mostly have, I believe it's helium, mostly helium. And then it inflates, it becomes as big as it does. There might be some other things in there too that might, push it that far, but basically it's going to be so big that it's going to engulf, the inner planets, and I think maybe Jupiter. I have to double check the size expectancy. But basically, you can expect the sun's technically getting bigger like every second. The corona, which is the most outer layer of the sun itself, can reach at least 5 million miles past wherever the sun's core is. And even though there are some planets that are technically within they're like what it's known as, because the sun has like roughly 7 layers, but like you can have like inner layers and you can have like an outer layer. So even like as far to the edge of our solar system's like 122 astronomical units, which if you don't know, that's 93 million miles times 122. One astronomical unit is 93 million miles. So basically, it's interesting to think that even like the Oort cloud, the perimeter of our solar system, is still within the sun's orbit. Because basically, a solar system is the circumference of a star's gravitational force. And our sun reaches out pretty far, actually. And so it's interesting to think that even planets that exceed that, they're still like, they still get the sun's light eventually, like, past Uranus, Neptune, Pluto, the Cupular Belt, however you pronounce it. It's it makes you wonder how many more objects are flying around in just this one solar system, or how many things have, like, if you're familiar with rogue stars and hypervelocity stars, things that just go flying out of their orbit. There's tons of planets and stars and galaxies that have a lot more of these than some other elements and moons and stars themselves. Well, it's not a no-brainer that some elements are also found on some other planets. Like, for example, elements that are found on this planet are also found on the sun. It's really interesting to think that when you really look at like the time, like the age expectancy of like stars and planets in just the solar system, a lot of scientists will agree that the sun is not really that much older than the Earth. But at the same time, though, it's interesting to think that the sun and the planets that are found in this solar system were formed basically in one of the same spots. And so it's kind of like that old argument where they say that the apple doesn't fall too far from the tree. And if you think of the tree as the sun and the fruits as the planets, you can basically get an understanding of, it does make sense that planets are made up of the same elements because they were like very close to each other, even though they're still a distance apart. So like, you find a lot of similar elements because elements are found in the same place. And there might actually be some undiscovered elements that we haven't found yet, even in just this solar system alone. Believe it or not, the sun actually orbits in its own way and rotates on its axis, and it takes approximately 27 days to make one full, complete stop. It's really interesting to think because objects in space move. Everything in space moves at a different velocity. Other planets might actually have different orbit speeds, rotations. They might have an even faster acceleration depending on how fast they're moving in space and whatever object they're rotating around and orbiting around. And it's just everything in space has its own motion. There really isn't such a thing that nothing in space is moving with all and if you really think about it, there's so many different kinds of unknown forces that are either due to speed or acceleration or some kind of just distortion, whatever that entails. And it's interesting to think that there might actually be more out, not only more out there that we don't understand, but like the physics and the geology of the universe. Just waiting to give like another definition of like how we perceive reality, rather. The orbit of the sun is also the same directional orbit as like most planets, although this isn't the case for Venus and Uranus, possibly, because what happened was when Venus was created at some point, it was actually hit really hard with like a really sizable object that ended up like kind of slowing down its magnetism and its rotation period. Because when you're looking at stuff in space, the direction it orbits and rotates, it's because the way it was formed in that planetary storm or something in its galaxy that caused it, depending on the motions it moves and the direction it rolls into. And so what's really interesting about the whole thing is if you were to take the way the direction of the sun orbits, because everything's orbiting around the sun, it also follows in the same direction because it's being pulled by its orbit and then the other accelerations that are following after it. So in theory, technically speaking, all planets would do the same thing their stars do, unless something disturbed said orbit that caused it to do something entirely different. So, like, for example, again, collisions like Venus. Uranus hasn't been observed as much, but it's quite possible that it might be, because we go in a counterclockwise position. However, the other elements, they go in a clockwise position, like Venus and Uranus do. But they still maintain their orbit that they've been doing for as long as they've basically existed. The solar system's mass is mostly comprised of the sun's mass entirely. And this is interesting to think about because the sun is very huge, in fact. But if we were to consider that, besides the Earth, the planets, and then maybe all the dark matter and everything that you find, it's interesting to think that most of the sun's mass is being used when you look at all its nuclear fusions and fissions because of how it works with the like how it moves in space and everything moves with it. It's burning most of it up, converting most of it to hydrogen and then converting it to helium rather. And over time, because of all this acceleration and all because of these ions forming, these subatomic particles burning, heat rather, friction in space. It's interesting to think that that's where most of the mass goes in the solar system because it's mostly being converted into other things. Because energy as we know it, everything's made of energy. Nothing is truly, there really is no such thing as nothing. I mean, it's just how much volume it has, and then it turns it into something else. Because like physical and chemical changes exist in that matter. If you have enough elements on a periodic table, for example, and you could take something and turn it into something else. Like, again, kind of like the definition of alchemy, for example, taking something in nature and turning it into something else, because you're converting this form of element into something else, because everything changes over a period of time. It's what is known as, like, for example, like a planetary evolution. Everything could change over time, because that nothing is truly the same when everything eventually goes through some kind of undergone evolution. And it's the same thing with this, most of the planet's solitary mass. The mass converts into something else over time, because every element might weigh something different, or maybe it might expand differently. Like, for example, helium, for example. If you have more helium than hydrogen, or vice versa, you're going to get different results because they all react differently. The sun is white, and the light that it gives off is also white. And what's really interesting about this, I didn't really think about this until now, actually, and it makes a lot of sense, because we're so used to seeing light mixed with other things. Technically speaking, and here's something else that's actually really interesting, there's technically an infinite number of colors, but there's a couple things to keep in mind. Everybody perceives light differently, and if you think about it, the way light works itself, the concept of light, photons, for example, mixes differently with other things. So you have to figure out how to convert light into something else, but at the same time, though, you have to think about how many different objects are being taken into consideration. So, like, for example, like all the pictures that they've taken with the sun, they couldn't just take a picture of a telescope. They had to send like a probe to the sun and then take a picture of it without it, because there would be so many different things you'd have to look through. Like, for example, if we were to use a telescope that was on this planet and it was looking at the sun in a different mode, they'd have to take into consideration that you're looking at, and be like looking through a prism of the sun, or through the atmosphere to the sun. And because, like, for example, like this planet's the light that goes off in our atmosphere, it makes it look like the sun is blue, because it's giving off different reflections of, like, the water, or it's giving off different stuff, the way our atmosphere works. It just other things mixing with other things. So basically, in theory, if you're trying to figure out like everything's true color, you basically would just have to go to that planet or that star, get as close as you can to it, and then try not to mix anything else with that object. Really, the only thing that separates the light between the star and the satellite would be like the dark matter that's around it. But because light doesn't mix with dark matter, it's not really much of a problem trying to take like a picture of the sun and then maybe convert it to something else. So then you could really examine the sun for what it really is, and you could see how they kind of got that white does kind of make sense, that the sun would be that, because maybe there's not too many things up there mixing with the radiation that it's burning. Because they say that, because even something else to think about, like a star itself, its colors can also tell you how hot it's burning. If I remember correctly, blue is the hottest color in a star's life. I think white is also up there, but I'm not sure if it's a cool color, but it could be a really hot color depending on how it burns, the temperature. But I mean, obviously stars that are super heated, such as like the sun, for example, the core of the sun is like 15 million degrees Fahrenheit, and it's because all the heat gets trapped within its core, because it's not just it could also have like a fiery core, but maybe it's just like a gas planet where it's just pure gas, but it's super heated, concentrated, and it's ready just to blow up after, because you got all these elements that are mixing with it that keep its core until it finally gives out. It goes out with a bang. All right, so this is interesting to think about. So the energy that escapes from the core to the outside core usually takes about 10,000 to 170,000 years inside the core. Basically, what this has to do is this goes along with 600 million tons of hydrogen is converted into helium per second. And so basically, what does this have to do with the way the system works is, over time, the like I said earlier in this video, like once all the hydrogen's gone, it's converted to helium. And so the sun gets technically bigger because of this. And what this really means is this is proof that our sun over time will become a red giant or a red supergiant, depending on. I mean, either way, it's going to be massive. It's going to be bigger than it technically is now. You could even argue that the sun increases in size over like every second. I think if my math is correct, from what I'm reading, they say that the sun's radius actually grows an inch every year because it's gaining more mass. The way the sun and again the special properties of said elements that cause things to just work in their own way. Again, if you have more, like I said earlier, like, you know, if you have more oxygen or more hydrogen than helium, it's going to be different than if there was more helium than oxygen, for example. And helium is a very inflatable, you know, gas element that can cause some very interesting things to, like a massive size ratio, rather. So over time, you're going to have a planet that's going to be eventually engulfed by its own star because there's going to be so much helium, rather, in the atmosphere or the core of the sun. And as it expands out, it gets even bigger, too. Because all that hydrogen is going to be converted into something else, but its properties will still be there, but just under something else, rather. And it's interesting to think that you really kind of get an understanding of just how big these stars really are based on what's inside of them. And I mean, for something that's burning like 600 million tons of hydrogen and helium, I mean, that's crazy to think about. Because 600 tons, 1 ton, if you think about it, is 2,000 pounds. And 1 pound is 16 ounces. And you're talking about these little elements that there's just so much of it. Subatomic particles, and it's something smaller than an atom, basically. And it weighs this much. There's so many, like, it's ridiculous. 600, so you'd say talking like 600 million times 2,000. And I mean, that's a way to go. So over time, it's like how many more elements are probably found in these stars that we don't even know about, that just to give off, it's just a giant heat source, and to stabilize the atmosphere so that the planet doesn't go flying out of its orbit. It keeps a steady balance between, so the stars go flying in space, but they fly in such a pattern that not only does it supply the planet with heat, but it also supplies it keeps it stationary, rather. So that way it doesn't become a rogue star and fly out of its orbit or fly into something else, basically. And it keeps its shape going, too, because over time, that's what gravity does to something spherical. You know, planets and stars are not true spheres in some cases, but at the same time, though, it's because of the orbits that they have and the gravity that feeds on it, that what it turns it into, rather. So, in other words, that's why, like, our planet is the shape that it is, because of its gravity, because of its orbit, but because of everything's like moving in a circle, rather. You know, what direction, and some planets might have weird orbits. For example, I think Pluto's probably the most notorious one in our solar system. It's really, even to this day, like, scientists don't really know 100% like what causes it. But at the same time, though, there's reasons to believe it's just because of how far it is away. So technically, in theory, the way it works is, even though there's stars that are, like, the further out you go, and depending on the more the star's mass is, the further out it expands. So the stronger its gravity is. But what's really interesting, though, is the further out you go, the weaker it gets, too. Because, you're so far out, but you're still in the atmosphere of the planet, or you're still within the orbit's gravitation of the star. And it's really interesting because, even though we humans have, for example, achieved some really outlandish things that, people would consider just massive achievements, Like, for example, I always thought it was amazing that, the further out you go, the harder it is to find some of these planets because their orbits are so far away. And, you know how, like, if you take a telescope and zoom in on it, even if you tilt it real slightly, it goes flying in another direction because you're still with that zoomed in ratio. And it's really interesting because properly trying to coordinate something with latitude and longitude and the sizable distance that it is, it can really make things a lot more interesting with the results you might find, because you have to figure out like where something is. And it seems like when you really look at like how somebody discovered something, it was like totally by accident, it seems like, because maybe somebody was doing like even like an observatory, somebody who's observing like stars, for example, or a planet, maybe they come across something totally by accident that they weren't even looking for, but it was like in that same direction of something else. And I mean, you see it all the time with like how they discover stars. Like there was a guy that discovered something totally by accident a while ago, and he was looking for a planet that he didn't even know even existed, and he ended up finding like another planet shortly after, and I think he found 3 more later that year. Because the way it works is when you're observing something, you write down, like, because scientists are always learning new things, so they keep their own notes, and then they report back to wherever agency they work for what they find, and they examine it latitude and longitude, and they come back to it later on. And it's interesting to think that over time, I mean, that's just how you learn new things, but how much you learn, though, because it's important to be accurate. And so it's like the same thing with the way these stars work. If we are to believe that these stars do this, that they get bigger, and there's much more stuff orbiting their orbital patterns, it really does make you wonder how much more is out there just waiting to be discovered, or how many stars, like, because within our lifetime, you really think that these stars are really not that big, but as old as they get, though, there's some stars out there that could live to be trillions of years old because they don't exhaust all of their mass. They don't exhaust all of they're not burning as fast or as hot. So you could technically have a star that could still technically create like a gravitational force where things could orbit around it and move in space. But at the same time, though, it's enough to create like a life structure where this planet can still exist based on its own, what inhabitants, rather. Like the planets that orbit around it. But, the planet could still be in a reasonable distance that it still exists, rather. It's crazy to think like how many possibilities you can have with just that alone. And at the same time, how much has passed in that time. We live only 100 years, if we're lucky. Maybe the life expectancy is a little lower. But, but at the same time, it's crazy to think like how many planets, could have existed, that maybe the sun might have engulfed, or maybe went flying out of its orbit, and we don't even know where those planets are at, let alone like what they could have been like in that time period. It's crazy to think how much stuff is lost to time and space. And stars like this can live, like, it's not going to happen with our star, but it's like, there's crazy to think that, there are some stars out there that live to be like trillions of years old, and they're still around wherever they're at. Or maybe some of them were unfortunate enough and they got sucked into a black hole, but like maybe transferred into another dimension, another universe. And because what's really interesting is, and this is what we really underestimate, and I want to tell people this because it's kind of why I make these videos. It got me really thinking about this, because even if energy is destroyed or changed into something else, it's not really truly destroyed. So that's really the trick there. It's really like it turns into something else. So every star that blows up, for example, like supernovas, or turns into a black hole, it's just being transferred into something else, somewhere else, into something else. One thing ends, but something immediately begins. Where at, how it works, it's waiting to be discovered. So many things that we're just waiting to discover, that it adds like some kind of a story. And here's just one of them. You know, here's like us, for example. Here we are on this planet, and we're still trying to figure out who we are and why we exist, because we're just intelligent enough to look around and say, hey, you know what? Maybe there is something here that nobody else really found yet. Fossils, or just another story that, or a question that somebody wants to dedicate their life trying to find the answer to.